So our next topic is fluid pressure and force, right? So we were studying about the force and pressure. So suppose cuboid is taken having height h, length l, and width is b.
So I have a doubt before we
Okay.
start.
First,
The
first, so consider a tank partially filled with water. So this is your tank having height h and length is l and width is b. Right. So if the pressure acting at the bottom of the tank is to be known, then it to be determined by the formula pressure is equal to HdG. P for pressure, H for height, D for density of water, and G for acceleration due to gravity. Right. If we put the height as 3 meter and density of water is 1000 kg per meter cube, then we will get P equal to 3 into 1000 into 9.8. Then it must be experiencing the pressure of 29,400 Newton per meter square. So this much of amount, how much pressure is experiencing this much, right? So now look at the next point. If the total force or thrust on the bottom of the tank is known, then the force or weight of the entire volume of the water. So weight is nothing but it is mg. Now we can put instead of m is volume into density. So instead of mass, we are putting volume into density. So it is V into D into G, right? In this way, you can also calculate. So F equal to, it will be volume is length into width into height and density we know, right? And put the value of G, you will get the answer of force. So read once this point. So next point is second, if the total force or thrust on the bottom of the tank is calculated by the weight formula, right? Weight is equal to mg. So instead of m, I have put volume into density, right? And volume is also further divided into area into height. So area into height is volume, and D is the density of water, and G is the acceleration due to gravity. Now take the dimension, arbitrary dimension. Suppose we are taking length as 4 meter, width is 2 meter, and height is 3 meter. Now put in the formula. So put LBH. So this is the dimension value, and D is the density of the water, and G is the value of acceleration due to gravity. So when we are multiplying all these three terms, all terms, then we are getting 2,35,200 newtons weight will be experienced by the water at the bottom, right? So in this way, you can calculate by using this formula, weight experienced by the fluid at the bottom. Your next topic is fluid pressure, shape, size of the container. A fluid exerts a pressure against any surface that comes in contact with it, right? So when liquid is following or flowing in any container, then any particles coming in that their path, then it will exert the pressure. Okay. Next point is when fluid is contained in a vessel, it exerts a pressure on the base of the container, and this pressure is not affected by the shape and size of the containers, right? So it only depends on the volume of the container, not on the shape. Like this type of shape is there, but it will not affect it, right? So pressure is not dependent on shape and size. So it is independent. So this must be coming in the MCQ. So, right, we will see the next experiment which will prove this one. So now look at the point pressure and force. So it must be emphasized that pressure is not as the same as force, right? Because pressure formula is force upon area and pressure is mn or mg. So these are the both different quantities, right? So while pressure is the ratio of force per unit area, but force is the product of pressure into area. So this is the main difference between them, right? If you want to write the formula, write this one and this one.
so I have already
So our next topic is, as we know, it is independent, right, of the shape and size. So we will see it by experiment. So you can see on right hand side, there are three types of container whose shape and size is different from each other. So this one is different from the second one, and second one is also different from the third one. So three container, each differing from the other in shape and size, and having neck on the same size. So this neck is same made for each three containers, but upper part is different. This part is different from each other now, but height is same for all three. So is filled with the same liquid and same height. So the neck of the each container is sealed with the rubber sheet and mounted in the test tank for measuring the pressure, and it is connected with the measuring instrument which can measure the pressure. So we know that pressure formula is HDG, right? So H is same for all the three containers. So we are putting H value same and density is same because same liquid is filled in all the three containers. And G acceleration due to gravity is same for all the three. So pressure coming out to be the same in the all the three containers. It doesn't depends on the shape and size, right? So third point indicates reading for the pressure at the bottom for each. Vessels are identical. So in this way, pressure is same for all the three. So result can be verified easily theoretically by applying the formula P equal to HDG. So P remains the same as height remains the same, right? And density is also same. So this experiment show that it doesn't depends on shape and size, pressure. It depends only on the height and density of the liquid. Now look at the next topic. Your next topic is pressure in gases. So air is a mixture of gases, right? So these gases form a band around the earth and constitutes the atmosphere. So gravity pulls the atmosphere down the earth, right? This is air pressure or atmospheric pressure, right? So suppose in air many types of gases are there, right? Oxygen, CO2, SO2, O2, right? H2O. So these are many different types of gases found in the atmosphere, right? So that pressure, that air, when it is closed in the container, it will exert the pressure on the wall of the container. So suppose this is the container in which I am taking O2 and H2. So mixture of this gas will exert the pressure on right, left, up, down of this container, right? That is called pressure exerted by the gas. Or when air in the atmosphere exert pressure on the human body or any substance, that is called atmospheric pressure, right? So now look at the next point. So atmospheric pressure is produced by the weight of the air at the top of the band as it presses down the air below, right? So pressure exerted by the air is due to the upper part or upper molecules of the air, right? So it will exert the pressure downward, right? Now next point, it presses on the surface of the earth with the force of about 1 kg on each square centimeter. So this much amount of pressure is exerted per centimeter square, right? And next, at the ground level, pressure is greatest because there is a large weight of air overhead pushing down. So we do not normally experience this pressure because the fluid inside our body exert an equal pressure outward, right? But the balance is done by atmospheric pressure. Our next point is the higher we go, the lesser air there is. So the pressure exert is less. So that's why we fly above the surface of earth, na? That's why, because pressure is less at the height. So the consequences of low pressure at high altitude is experienced by the mountaineers, right? And breathing becomes difficult since the greater pressure inside our body would prevent the intake of the air, right? Because when we are at the highest point, pressure inside our body is high as compared to the environment at the maximum height. So So we feel difficulty to take the air inside. Our next point is blood capillary may also rupture and causing the noise and ears to be bleed. That's why we bleed at the when pressure is less. That is why aircraft flying at high altitude must have pressure cabin, right? So that's why pressure cabin is made for the aircraft. And now look at the next explanation here on the right hand side. Initially, the shape of the thin container is maintained as the pressure inside the can is same as the air pressure outside, right? So initially the shape of the container is maintained because pressure inside can is same outside. And now when water is filled and boiled, this will drive out much of the air, right? When we are boiling this water, so water vapor will come out from this cap, right? And the pressure of the steam will still equal that of the air outside because this will maintain the air pressure and outside is same, right? So read once. Our next point is before the experiment, your container is looking like this, right? And after the crust cabin or container is looking like this. So earlier scientists thought that atmospheric pressure was simply the weight of the hundreds of kilometers of air, right? Pushing down the earth on downward. In fact, air pressure pushes the air in all direction, upward, downward, and sideways. So it is a constant bombardment of the moving of air molecules, right? Because air particles move in all the three direction, x, y, z direction. So pressure is exerted on the all the three dimensions or all the three coordinates axes, x, y, z. So because air molecules in always in random motion, right? So they are having kinetic energy 1 upon 2 mv square. So this is the pressure exerted by the gas particles because they are always in random motion. And look at the next point, replacing the cap prevent entering of the air as the steam tube cools and condenses to water. A partial vacuum is created. So outside the pressure is now greater than that of the inside. So that's the can be crushed. So suppose we are want to crush this can, so pressure of inside will be lower as compared to outside. That's why we can change the shape of the can, right? Now look at the Medberg experiment. So for thousands of years, scientists thought that there would be no such things in vacuum. So a space with nothing in it. So in 1644, Evangelista Torrelsi succeeded in creating a vacuum in the tube, right? So he created the vacuum in the tube because in tube air particles is evacuated from the torricelli and vacuum is created. Vacuum is nothing but there is no particles or any gases is there. So now look at the next point. In 1654, Otto van Durice, a German engineer and mayors of towns of Medverz, invented the first air pump with which he evacuated a copper sphere. The two hemispheres were joined only by a leather washer soaked in wax and turpentine. Doriski used to demonstrate the strength of atmospheric pressure, right? So in 1654, Toto von Giudici, a German engineer, mayor of the town of the Medberg, invented the first air pump, which he evacuated the copper sphere. Two hemispheres were joined by a leather was soaked in vacuum and turpentine, right? Used to demonstrate the strength of atmospheric pressure. So a team of horses were attached to each half of the hollow sphere. Even 16 horses could not pull the hemisphere apart. Right. When vacuum is created, so they are not able to pull the this one, right? So you can see this is the copper pump in which horse is connected to each other to cool that. So when there is vacuum, so large amount of pressure is experienced by them. So now look at the common application. So a common household device that uses air pressure is the rubber suction pad used on wall to hang clothes and calendars. So this is the air pressure application in which we hang our clothes, right? Because it creates a vacuum, rubber suction. And when moistened and pressed against a flat surface, air is forced out, so reducing the pressure inside. So when moistened and pressed against a flat surface, air is forced out and reduce the pressure inside, right? And outside pressure being greater, the sucker is pushed firmly down and it adheres to the surface, right? So due to this, that air rubber is hanged out and which is used for the hanging the clothes, right? Next one is lizards are able to adhere to the wall because of their feet function like suction pads, right? We can see the lizards walking on the wall of the our houses due to the atmospheric pressure because it creates the vacuum inside the its leg or feet. So now look at the strength of air pressure. So spread a piece of aluminum foil at the bottom of a plastic cup to prevent it from getting the scorched. So this is the strength we can provide to the air by using air pressure application. Now drop a light matched stick into the cup and quickly cover the mouth of the cup with the floating paper soaked in water. Right. So this is the main application of pressure. So please read. Look at the third point. Third point is now invert another similar cup exactly over this. So this is another cup and this one is another one, right? So after the match is extinguishes, lift up the top cup. So you will find that bottom cup remains attached to the top cup and lifted up along with it, right? Due to the vacuum, up downward cup is uplifted up due to the vacuum created. This is because as the much burned, it used up some of the air, oxygen inside the cup, therefore creating the partial vacuum, right? So suppose match is burning here and we have covered this with another cap and this match stick uses the oxygen inside this cup. So due to the less air inside it, vacuum is some created. That's why it is lifted when we are lifting it, right? So now our next topic is measurement of pressure. It is measured by the barometer. So barometer is a instrument which measures the pressure, right? So barometer is instrument that measures the pressure of the atmosphere, right? So this is the mercury barometer, right? This one. So we use mercury for the measurement of the pressure outside the atmosphere. And this is torrencial vacuum here created, right? So now look at the principle of barometer is used to measure the atmospheric pressure to balance the vertical column of the mercury sealed at the top. So it is sealed with the this one sealed at the top so that we can measure the atmospheric pressure by using the mercury as a sensor. So simple barometer. So fill a glass tube about of 100 centimeter long with the mercury and the open end is closed with the thumb. So here we are holding our thumb and the tube inverted and held upward. So after the open end has been placed beneath the surface of some mercury, in trough, the thumb is removed, right? So level of the mercury in the tube drops and leaving a space above called torricellium vacuum. So here vacuum is created by putting downward. It contains traces of mercury vapors. So in this way we can measure our pressure. So height of the mercury indicates that atmospheric pressure. So every 110 ascent, so there is a fall of 1 centimeter of mercury in the column. So by using this much, this reference point will give the atmospheric pressure, right? So this is the simple experiment through which we can measure the atmosphere pressure, right? So read this experiment. So our next point is, uh, so I have explained this one, right? So for every 110 ascent, there is fall of 1 centimeter in the mercury column, right? So as the atmospheric pressure changes, so does the height of the mercury column also changes. By measuring the height of above the surface of the open ball, atmospheric pressure can be determined. So in this way, atmospheric pressure is calculated by barometer. Now look at this diagram. So vertical height of the mercury column doesn't depends on the shape or size of the tube, right? So as we have discussed earlier that liquid or pressure is doesn't depends on the shape and size, right? So height of the doesn't change even if tube is tilted because pressure is only HDZ. So it doesn't depends on the size, shape and angles. So when it is tilted, height will H, pressure is same for the same point. So this A, B, C having height, same height H. So pressure exerted at A, B, C will be same even if this tube is tilted, right? With the some angle.